You can freely download this practical notebook from my website. From its home page, go to middle left and click Books and Notes. A new web page will open. Then download third book in PDF format. Experiment 8 on page 39 in the practical notebook. Left side page of same experiment.
Hello, I am Iftikhar Hussain. Today we are going to perform an experiment. The name of this experiment is to verify the second condition of equilibrium using suspended meter. In order to verify the second condition of equilibrium mathematically, it shows that sum of all the torques acting on a body, it must be equal to 0. That is, sigma torque must be nearly equal to 0. In order to verify, to prove practically is it true or false, our step 1 is we will find out the center of the gravity of this meteor as shown in the diagram. To find out the center of the gravity of the meteor, we will place our meteor on the sharp edge as shown in this diagram. Now we are going to balance this meteor on the sharp edge from both sides. The point at which it is balancing on the wedge, that point represents the center of the gravity of this meteor, as shown as it is demonstrated practically. We will take this wooden sharp edge and place it on some horizontal surface like this one. Then we will use this meter rod and we are going to balance this meter rod on the sharp edge like this one. Look at here. So we will place this meter rod vertically, not horizontally. This is a wrong way. This is a correct way. So we are balancing this meter rod on the edge of this wedge like this. So at a point where it shows the balance, that point will be taken as the center of the gravity of this meteor. So like this one, this is a balance like this one. So it is balancing approximately at its middle point. Look at it. So not this point. So this point will be taken as the center of the gravity of the meteor. So position of the center of the gravity of the meteor, that was 50.1 centimeter. Our next step is we want to find the weight of the meteor practically, and for this purpose we will set our apparatus as shown in this diagram. Diagram represents these are two stands. This is a meter rod. S1, S2 are the spring balances. W is the external weight. Small w will represent the weight of this meter rod when it will be balanced with respect to this diagram. So now we are going to measure the weight of this meter rod practically. These are the spring balances which we will use in our experiment to calculate the values of the forces, because mathematically we know that sigma torque is the product of force and the moment arm. So force is measured with the help of these spring balances, and the moment arm will be measured with the help of the meter rod. So you can see On this spring balance, there are two scales. On my right hand side, the scale represents the measurements of the forces in Newton, whereas on left hand side, the scale represents the measurement in grams. So for our convenience, we will take the measurement of the forces in gram weight. Also, you can see their first one, also to take the readings with the help of the spring balance, we will check is there is any zero error present on this spring balance. What is zero error? Basically, this pointer and the zero line of the scale, it must be in coincide. If they are not coinciding with one another, with the help of this point, you can remove the presence like this one. You can remove the zero error from your this spring balance. Again, we'll check it. The pointer and the zero line, they must be coinciding with one another. Next, you are suspended these two spring balances on these stands like this one. Performing our experiment, and for this purpose, as you can see the observation from your book, we are basically measuring the weight of this meter rod, and this is a way in which we will suspend this meter rod with the help of two loops of thread horizontally like this. Now we will set our apparatus. The distance between these two spring balance S1 and S2 must be proper. The positions of these threads, it must be vertical. This is a wrong way. If you are setting your apparatus like this one, so it will produce the error of considering in your experiment. Similarly, if you are suspending your meter rod like this one, again this is a precaution, or you can say error in reading. So the correct way is, first one, always suspend your meter rod like this one, and the position of the loops on this meter rod, it must be vertical. Now we want to balance this meter rod horizontally. We are measuring the weight of this meter rod. You can see that this meter rod is unbalanced because its vertical height from this table is not equal. To make it balance, we can adjust, we will lose these screws and will adjust the meter rods like this one. We will take the help of another half meter rod in order to measure the vertical height from this side and this side. It must be equal. Still, this height is a little bit high from this edge. So similarly, now check it. Now you can see that the height of this meter rod from both ends is equal with respect to this table. Now we can say that now meter rod is balanced. And you know that in your physics, when a body is balanced, it means the sum of all the forces which is acting on this body downward and upward, they must be equal. And this is known as first condition of equilibrium. So when we will when we will balance our meter rod, so we will measure the weight of this meter rod with the help of spring balance S1 and with the help of spring balance S2. So now we will measure the weight of this meter rod with the help of the spring balance S1. This is S1, is supposed to be spring balance S1. This spring balance is S2. You can see after balancing the meter rod, when it is in balance condition, you can see the reading of the pointer on the scale. Now it is not at 0. It represents at the mid of the scale 0 to 100 grams. And using your calculations, this pointer is at mean at 50 grams, and this pointer, which is S2, it is at you can see 0.8 or at 80 grams. So the position of this pointer is 50 grams, and the position of this pointer is at approximately, you can say, at 80 grams. So the sum of these two readings, one is S1, second is S2, that will be equal to the weight of this meter rod. And we know that the weight of a body is acting at the center of the gravity of that body. So here the body is a meter rod, so its weight is acting at this point, which was measured step 1 with the help of that placement of the meter rod. So its weight is acting, W, small w, is acting at this point, so it is equal to the sum of this force, which is P upward, and this force is Q upward. So now by adding these two values that represent the weight of this meter, you can see on this spring balance the pointer is at 70 grams, whereas on this spring balance, which is S2, the position of the pointer is also at 70 grams. So sum of these two forces, P and Q, that is equal to the weight of this meter rod. Okay dear students, now we are going to take the observations, because again keep this point in your mind, we are practically verifying the conditions of the equilibrium. So for this purpose, now we are taking an external mass. Say this is capital W. Its mass is 100 grams. So for simplicity, this weight, the weight of this body is taken to be 100 gram weight. We will place this weight with the help of this loop. So we will remove and we will place this external weight on this meter rod, and again we will place this loop at the same position. We are placing this weight, that is capital W, at the center of the gravity of this. You can see again, by adding a weight at the center of the gravity of this meter rod, the readings of the pointers changed. It means downward force is increasing, so automatically the upward force will also increase. In order to again check the balance of this meter rod from both sides, again we'll take the help of this meter rod and note down the horizontal position at this point, and similarly from this point. So the heights are equal from both sides. So we are balancing it. This point is very important, that in order to verify, to prove the conditions of equilibrium, the meter rod must be balanced from both sides. So according to our observation and calculations, now we are using some names for the positions of three forces which are acting on this meter rod. I say three forces. What are these three forces? One is at point A, second is at point B, third force is at the center of the gravity. If this meter rod is balanced, it means using your first condition, the sum of all these forces, it must be zero. Pivot. And for this purpose, the starting position, one end of this meter rod, means the starting position of this meter rod is taken as the point of the axis. So from this point, this is taken to the point of axis C. So C to A will be the moment arm of this force P, which is upward. C to this point G. G is mean center of gravity. This is known as the moment arm of this force, which is downward. And similarly, from C to B, this point is a B, supposed to be B. This distance will be equal to the moment arm of the force Q. So we will now note the values of the forces and the momentum. So first we will take the reading of the force P on spring balance S1 and the position of the pointer on S1 shows that the force which is acting at point A, it is equal to 110 gram weight. Similarly, the value of the force which is acting at this position upward, the pointer or scale of spring balance S2 shows it is at 120 gram weight. Third one is the force is downward, as we have measured, it is mentioned. This force is 100 gram weight, is acting at the center of the gravity of this meter rod. Now we will measure the moment's arm. And you know that by definition, what is the moment arm? It is a distance between the point of pivot and the point of the action of the force. So diagrammatically, practically, this point is a point of pivot. So from this to this position, which is 22 centimeter, 22 centimeter is the moment arm of the force P. From this to center of gravity, which is 50.1 centimeter, C to G, that is another moment arm of this force. And similarly, from this point, the point P is at 80 centimeter. This is the moment arm of this force Q. So this force will produce a counterclockwise torque. Similarly, this force Q will produce a counterclockwise torque. Whereas this W, weight of the meter rod, plus this external weight, this force F will produce a clockwise torque. So theoretically, the sum of these three torques, it must be equal to 0. But when we are observing, when we are performing an experiment in our lab, so there are some limitations. What are the limitations? It means the calibrations of the spring balance, the density, or you can say the mass of this meter rod, it may be non-uniform. Similarly, there are some sources of errors which are present in our practicals. We want to just verify the answer is nearly equal to 0. It cannot be equal to 0 practically. Again, the reason is because the sources of errors are always present in the practical. So now you will take the readings. What is P? What is Q? Moment arm of the force P. Moment arm of the force Q. Moment arm of this weight W, which is F. What is F? F is basically the sum of two forces. One is the weight of this meter rod, and the second one is that weight which you are hanging at the center of the gravity. So you will take these readings, and again you will take the help of your table by putting the values of P, Q, F, C to A, C to B, C to G, and then by multiplication mean torque 1 is basically equal to P into C into A. It is counterclockwise torque. What is torque 2? It is the product of this force P into C into B distance. And what is torque 3? It is equal to the product of force. What is F? Again, this point is very important. As given in your table, in your copy, this force F is equal to the weight of this meter rod plus this external weight, which is we are taking in ground weight. So by using your tables, multiplication and calculation for your first observation, you can check your answer. Is it nearly equal to 0 or no? If your answer comes out to be 0 in this way, by performance, by exactly balancing, by removing the 0 error in your spring balance, you can see that your answer is nearly equal to 0. If it is not comes out to be 0, it means either you are ignoring the 0 errors which are present in your spring balances, or your meter rod is not balanced with respect to your horizontal table. I am taking just only first observation. Similarly, you will just replace or add some weight at this position. You will take 2, 3, 4, 5, 6 readings, and in each reading your answer, your verification is sum of all torques must be nearly equal to 0 within the limits of your experimental lab. So our position of the center of gravity of the meter rod was 50.1 cm. When we did the balance of our meter rod without an external weight, the weight of the meter rod was approximately 40 gram weight. For measurement of the torque, we need the axis of rotation, mean one end of the meter rod, that point is C, which is starting, that is 0.00 centimeter. In order to verify the condition of equilibrium, we need 3 observations. So I am taking just only one observation for your convenience. So this table represents the amount of the forces which is acting on this meter rod, momentum and torque about the center of the gravity. The last column represents mathematically sum of torque, means measure of the torque which is acting on this meter rod. So our first force was 30 gram weight, which is P acting on S1. Our second force was again 30 gram weight, which is acting on spring balance S2. This F is very important. This point is very important because this force is equal to W plus W. This is a capital W, this is small w. What is capital W? The external weight, and the small w is the weight of the meter rod. So 20 plus 40, this 40 will remain same. We are just increasing this external weight at the center of the gravity. For our convenience, again, we are measuring the momentum of the force P, which is 30.2 centimeter, the momentum of the force Q from the axis of rotation, that is 66.8 centimeter, and the momentum of the force is acting at the center of gravity, it is 50.1 centimeter. So torque about G, 2 torques are counterclockwise, mean anti-clockwise, and 1 torque is a clockwise. Counterclockwise torque again is equal to P into CA. T1, T2, T3, these are 3 torques and they are represents in the diagram. So torque 1 is a counterclockwise, which is equal to the amount of force P into its momentum, CA. So gram weight centimeter will be the units of this torque T1. So what is P? That is 30 gram weight. CA is the momentum of this force after balancing, that is 35.2 centimeters. Similarly, a counterclockwise torque T2, it is equal to again 30 into 66.8. This 66.8 is the momentum of the second force which is acting at spring balance S2. Torque 3 is again equal to 60. What is 60? Which is sum of 2 weights. One is the weight of the meter rod and second is the external weight. So 60 into 50.1 is the position of the center of the gravity. So sum of these 2 torques must be equal to this torque, or you can say by summation like this one, you can write in the equation that sigma torque is equal to torque 1 plus torque 2 minus torque 3. these two torques are anti-clockwise, this torque is clockwise, so their sum is nearly equal to 0. It is our first observation. In our second and third observation, we will just increase this capital W. We can keep CA, CB, CG as constant. We can also change the positions of these pointers. Pointers mean the positions of these loops, because mathematically simply torque is the product of force in two moments arm. So any one parameter change will produce a change in the results. So just in our second and third observation, we will increase just W at the center of the gravity, and we can check what is your answer. So at the end, which is verification, what is the verification? So in our experiment, we are verifying the sum of all torque, it must be equal to 0. So within the limits of your experimental error, because I have already said the source of our errors are always present in our practical, their sum is nearly equal to 0. This is our whole experiment.
You can take this book, Objective Physics Practicals, from Ilmi Book Depot, Urdu Bazaar, Lahore. Your readings may be different from these readings. Check these readings as a reference. Thank you.